So let's continue with the class and discuss what we were, where we left off. So let me do a small recap. We covered a lot of stuff last class, but I only want you to understand most of it qualitatively rather than quantitatively. Okay, because some of these derivations can be a little bit complicated. I will just briefly outline some of the key features of what we did last class, which I want you to remember. Okay, so firstly, what we did was we talked about the phase average of a quantity. Okay, and we said that it is equal to, if you knew the functional form of that particular physical quantity as a function of q and p, the generalized coordinates and the generalized momentum, and you knew this function rho, which is also a function of qp and maybe explicitly a function of t, then is basically the phase average of this particular quantity, as this system is actually sampling the phase space, the various points of phase space. This is one way to basically write down the phase average of this particular quantity. And we the reason why we brought this into picture was we had another expression that looks something like this, right? Limit delta t tends to a very large quantity 1 over delta t, integral a of q of t comma p of t dt, right? And for this, in order to evaluate this particular quantity, it is important for us to know how q and p evolves with time. And for a complicated system comprising of a very large number of atoms, it would be impossible for us to theoretically solve these solve for these unknowns, solve for the variation of q and p with time. So we take a different approach called as the phase space approach, where we say that we get this quantity, and this quantity we wave our hands and say that this quantity, the phase average and the time average, have to be equal. Okay, there are proofs or there are arguments that can be made in order to say that these two are equal, but it's not too hard for us to intuitively understand that if we take a large number of points in phase space, it is most likely to get all the points that p and q are traversing even with time. Okay, in molecular dynamics simulations we generally use the time average, but in statistical mechanics we generally talk about this phase average. Okay, now this phase average gives additional useful information. Primarily, we said that if this quantity average of A has to be independent of time, then it kind of implicitly implies that this density function should also be not be explicitly dependent on time, right? We made this statement, and I would like to now point out that such a ensemble for which rho does not depend explicitly on time is called a stationary ensemble. Okay, so if rho is not explicitly dependent on time, it's called a stationary ensemble, and obviously a stationary ensemble is a good ensemble to have to depict systems which are at equilibrium, simply because this average quantity does not vary with time, which is what our observation tells us. Okay, now then we switched gears a little bit and wrote down this equation right here. We wrote down this equation right here, right? And we said that this has to be 0, correct? We didn't prove it, we just told you that this has to be 0. Okay, and we kind of compared it with the mass balance equation, and talking about incompressible, the points in the phase space move like an incompressible fluid. Okay, so if this is anyway 0, this is always 0, and we want dou rho by dou t also to be 0, right? Then one of the condition that rho must satisfy is that this quantity must also be 0. This quantity right here in which I have marked, right? Now for this quantity to be 0, for to be equal to 0, what must happen? We said that rho can either be a constant or if rho happens to be an explicit function of P and Q only through the Hamiltonian, even then this turns out to be 0, right? Remember this? So these are the two conditions for which this term here turned out to be 0. Okay. Now this is something that we can derive right now. Okay. It so happens that the probability density, this is nothing but the probability this is nothing but the density, right? Number of points per unit volume, and the probability density which we will now represent using f is nothing but rho of q comma p divided by integral rho of q comma p dq dp, right, integrated over the entire phase space. This is number of, the numerator here is the number of points per unit volume. This is the total number of points, right? So number of points per unit volume divided by total number of points is some kind of measure of the probability density, the probability that a certain in a certain given volume dp dq you find the value pq. That's what it means, right? What we are going to try to do now is we are going to see under what conditions, or I am going to tell you under what conditions rho happens to be explicitly dependent on h. Okay, and for conservative systems, h or the Hamiltonian is nothing but, what is it? What is h? T plus V. So the kinetic energy plus the potential energy, and is nothing but the energy, total energy of the system. For conservative systems, the Hamiltonian is nothing but the energy of the system. Okay, so what happens is that you can find out that this rho is apparently a dependent explicitly on the energy of the system. Okay, that's what we are going to do now. So this happens to be the case for the NVT ensemble or the canonical ensemble. Okay, so whether rho is explicitly dependent on h or f is explicitly dependent on h, it doesn't matter, it all means the same thing, right? So now how do we do this? So first I am going to do this derivation where I show you that this rho explicitly dependent on h or f explicitly depends on h or the energy through a simple intuitive means, and then we will do a slightly different approach giving us exactly the same result. Okay. Okay. So let us consider the microcanonical ensemble. Sorry, the canonical ensemble. I mean the canonical ensemble. The canonical ensemble represents a system at with constant number of atoms, constant volume, and constant temperature. Okay, so this is our system here, N, V, and T. Okay, so it may be at some arbitrary temperature initially, but what we are going to do is we are going to take this entire system and equilibrate it with a large reservoir. So this is our N, V, T. Okay, and this is my N prime, V prime, and T. Okay. So this is a large reservoir which is also, and isolate these two systems. What is that? So they are both in thermal equilibrium with each other. We are waiting long enough so that, so basically this large reservoir is at temperature T. So if we have to bring this smaller system to temperature T, we just put it inside and wait until equilibrium has been reached. Okay. This is very large. So now at any instant of time, so the question that we want to ask, okay, the actual question that we want to ask is, what is the probability that this system that is there right here has an energy EI? What is the probability that the system has an energy EI, or in other words, has an Hamiltonian corresponding to some QI comma PI? Both are the same questions, right? Because energy and Hamiltonian are the same things for conservative systems. Okay. So what I am going to do now first, at any instant of time T, okay, the system may have energy EI, okay, and the reservoir could be having energy EI prime, right? However, the sum of both these energies can be in any of the various available microstates compatible with the energy EI prime, right? The reservoir by itself can have various different, it can be with energy EI prime, but have so many different microstates, right? So let omega EI prime be the total number of microstates that's possible for the reservoir. Okay. Now, so the larger the number of microstates, right, for this particular energy EI prime, the greater is the probability that you will find the reservoir in the energy state EI prime, which means the greater the probability that you will find the system at energy EI, correct? So Pi, which is nothing but the probability that the system is at energy EI, is actually proportional to this quantity EI prime. Okay, and this EI prime, remember, is extremely close to E naught because of the sheer size of it, right? It's a huge reservoir, which also means, for the purposes of getting specific thermodynamic quantities, I am going to write it as this, okay, which is the same. I have just taken a logarithm on both sides. Now I can expand this quantity about E naught, yes? Okay. So omega EI prime is the total number of microstates that the reservoir is in. Okay. The larger the number of microstates available for the reservoir to be in EI prime, the greater the probability that it is actually in EI prime, or which essentially means the greater the probability that the system is in energy EI, because EI prime minus E naught is EI, isn't it?
Because EI prime, then there is less probability that it's EI.
The system is in EI because E naught is a constant, right? If omega, the greater the probability that the reservoir is in the energy EI prime, the greater the probability that the system is in energy what? EI, not anything else. Yes? So that we can write an expansion about E naught. As you will see, like I told you, this is a simpler version of the derivation that I am about to show after this. Okay, the reason is if you expand, basically you get the expression more quickly than through a longer procedure. So that's it. Okay, so if you take this ln of omega ei prime and expand it about E naught, what would you get? Ln of omega evaluated at E naught plus dou ln omega E naught with respect to dou ei prime multiplied by ei prime minus E naught plus higher order terms, right? And I continue here, this becomes ln of omega ei prime is equal to ln of E naught. So this now what is this? Ei prime minus E naught is what? Ei prime minus E naught is minus of Ei, right? Ei prime minus E naught will be minus of Ei, minus of Ei, and what do you think this quantity is? Dou ln omega E naught by dou ln Ei prime? No, it's not very less, it's a thermodynamic quantity. The number of microstates with respect to ln of the number of microstates with respect to the energy. We have seen that before. Dou ln omega by dou E beta, that is the beta quantity or 1 by kT quantity, isn't it? So, however, that is true provided again I approximate this as dou ln omega of Ei prime with respect to dou ln Ei prime, right? Because I am saying that, I am waving my hands and saying that E naught and Ei prime are pretty close to each other. Consequently, this becomes beta. Okay. So what you get here is the ln of Pi, the probability that the system is at energy Ei is proportional to this quantity right here, ln of omega E naught minus Ei times beta, again which means Pi is proportional to omega E naught times exponential minus Ei times beta. Now again I can include some sort of a constant here is equal to A omega E naught exp minus Ei beta. However, what is this quantity? Summation of probability that it is in any energy Ei is 1, which implies that A omega E naught summation over all energy states is equal to 1, or I can substitute, I can find out what this A omega E naught to be equal to 1 divided by summation over I, or the probability that the system is at energy Ei is right. Is this okay? We will do this in a slightly different way also. This can also be written as probability that I find a certain Q and P to be equal to exp minus beta, the Hamiltonian at Pi Qi divided by I exp minus beta okay, this is the probability, actual probability. So this is the probability that you find qi pi, right? Now we can write the following, we can say f probability density times some infinitesimal volume element in the phase space dq dp is actually equal to pi, right? Probability per unit volume times the unit volume is going to give you the probability, correct? Now this is equal to this quantity right here, which means f of qi comma pi is equal to okay. So this summation, is this okay? This sentence, this particular expression is all right. Probability per unit volume times the unit volume must give you the probability, right? So that's what is pi, which is which is basically the right hand side. This exp minus beta h divided by summation over all the other states. Therefore, this f probability density is supposed to be this quantity right here. I just brought this dp dq here. Okay, you might, if you are very rigorous in your mathematics, you might crib. Okay, but we have to do this in order to make the expression appear correct in a simpler manner. Okay, so now this f qi pi is equal to, now this summation is assuming that this pi's and qi's are all discrete quantities. However, in phase space they can all be treated as continuous quantities in phase space, right? You have p's and q's so close to each other, they are almost like a continuous set of points, right? They are all moving from one point to the other through time, right? So we can replace this expression by the following. So this is a probability density, means a probability per unit volume that you can actually find a point qi pi, and it depends on what? The Hamiltonian or the energy of the system, which is the same as, this is the same as rho qi comma pi divided by integral rho qi comma pi dq dp, which means the rho is proportional to exp minus beta h qi pi, or in other words, rho is proportional or a function of, is proportional to a function explicitly of the Hamiltonian of the system. Okay, so this is one way of showing that the most important quantity here is this: the probability that you find a system at energy EI is given by this. So if a system is at NVT, you are maintaining the number of atoms or the number of atoms, the volume and the temperature of system. Then if you ask the question, what is the energy, what is the probability that the energy is something, some k joules, then this expression is giving you that, the probability. Okay, so what would be the, what is the average energy of the system? So the average energy of the system or any quantity is nothing but integral the energy ER times F. or the average energy is nothing but the Hamiltonian probability that that particular P and Q occur, and this is nothing but this. So you have to substitute this here and perform this integration to find the average energy of the system, which is what the system's energy will be at what? Equilibrium, right? But we are not going to do these calculations, okay? It's enough if you know that this is how it appears. Now we did something, and I'm sure you had questions about why we did this in a, you have some question? Oh, I'm going too fast, okay. Okay, E is the E of Q comma P. The energy of the system at Q comma P, and F gives you the probability per unit volume that a Q comma P can be found. Integrated over the entire phase space is going to give you the average energy of the system. Okay. So E of Q comma P or H of Q comma P is nothing but half mv square plus the potential energy of the system. So you can, in principle, now if you want to find out the average energy of a gas at a particular temperature T, you can find it out by just substituting for H the kinetic energy of the system. Rho and F. Rho is the number of points per unit volume. That's rho. F is number of points per unit volume divided by total number of points. Therefore, it's a probability density. Rho is number density, number per unit volume. That's the difference. Correct? Yes or no? A second thing that you can look at is, again, what is this? This denominator here is what? Integral of rho qi pi dq dp must be proportional to the total number of points. It need not be equal to the total number of points, right? It's proportional to the total number of points, because a common factor of the numerator and denominator may have cancelled out when we calculated the probability density, right? So this omega is proportional to this quantity right here. So once I put this thing, we should not write right? It's just rho of P comma Q, not Pi comma Qi, right? So now what is the proportionality constant? I think we already did this, right? This omega has to be commensurate with the omega that we find using quantum mechanics. So which essentially means that n factorial, you have to divide it by n factorial and h power 3n in order to get the correct enumeration of the microstates. We saw this in the last, at least we mentioned this in the last class, right? So you got to keep remembering this expression. This expression is integral exp exponent minus beta h will occur several times when you are working with statistical mechanics. But because every time you want to find out the average property of anything, okay, say for example, you want to find the average Cijkl. Okay, I don't know what that expression is, but just to illustrate, if you knew explicitly what the expression for Cijkl is, or the elastic constants of the system as a function of Q and P, then this has to be multiplied with this quantity right here, exp minus beta, the Hamiltonian q comma p divided by, or f, okay, this and this entire thing would tell you what is the average of the system. Okay. So, to if you are able to perform this integration explicitly, then you would get an explicit, say, some function, right? Some function of q and p, right? You would get some function of q and p. Now let us try another way of deriving the same thing. Yes, you had some questions? Suppose we have the Helmholtz free energy as a function of q and p and the strain as a function of q and p. Then we may theoretically differentiate this Helmholtz free energy with respect to the strain, right, and get the stress, right, as a function of q and p. Now if you differentiate this, you basically get as a function of q and p, explicit expressions for q and p. You substitute thisCijkl, q and p here in this expression right here and perform this integration, you would get the average elastic constant the system will have at equilibrium. But for molecular dynamic simulation, the beauty is, it is enough if you have this. For molecular dynamic simulations, it's sufficient if you have this, because you are only going to perform a time average, right? But we definitely need at least an expression for A and E in terms of Q and P to be able to find out sigma and hence find out theCijkl in terms of Q and P. Once you find expression for Q and P, you can do time averaging. In molecular dynamic simulations, what you can do is you can do this. So, limit over long time, integral over 0 to delta t,Cijkl, q as a function of time, p as a function of time, dt. Can be done in order to calculate the time averaged. So, for time long enough, we say that the time average and the phase average are both equal. This and this are both equal. Okay. So, it's a good idea to look at. We will spend some time in actually rederiving this expression, the probability that a system is at energy EI, through a slightly different means, slightly probably a little bit more intuitive than the derivation that we just did now, and then we will derive how the Helmholtz free energy can be written as a function of Q and P. Okay. So, the ensemble approach. Okay. So, let us consider the system having N, V and T. Okay. Now, let us assume that a large number of these systems, each of which is in a slightly different microstate, however in the same macro state, they are all put together, exchanging energy with each other, and the entire thing is put inside a bath and isolated from the surroundings. Each is the same system, it's having the same number of atoms, same volume, same temperature, but it is in a different microstate. It's in a different microstate. It means the P's and Q's are arranged such that NBT is the same, but E and all could be different. Okay. Once again, the question that we are going to ask is, what is the probability that a system can be at energy EI? Same question we ask, what is the probability that the system is having an energy EI? Okay. So, if you want to find this, what do you need to do? Actually, what is this expression? You know, from basic thing, it is nothing but the number of systems. Okay, let me use A. So, the number of systems with energy EI divided by the total number of systems that is present here. That will give me the average number of systems. What is the probability that the system is at energy EI? Right. So, this n is extremely large, huge number. Okay. So, in order to get this probability, in order to find out this probability, we have to first enumerate how different ensembles can be put in different energy levels. So, let us say that there are energy levels E1, E2, E3 and so on till some energy level EE. Okay. And one possible distribution is that there could be, say, A11 number of ensembles in energy E1, A21 with energy E2, A31 with energy E3 and so on, and E1 with energy EE. Okay. We also, before I proceed further, I need to make sure that the total number of is n. So, if you count them, they have to be n, because we have taken n different ensembles. So, there is a constraint there. The second constraint is that the energy of each system. So, if EI is the total number of is the energy, and AI is the total number of systems with energy EI, then this entire thing has to be some constant energy E, right, because I have just put everything together, right. So, these are the two constraints that this system has to satisfy. So, one way, this is one way the system can have some energy distribution, right. So, there can be a certain number of systems at energy E1, certain number of systems at energy E2 and so on. So, we will call this distribution as, say, the A1 distribution. Okay. There could be another distribution which I am going to call as A2 distribution, where A12 is the total number of systems with energy E1, A22, A32 and so on, AE2. Similarly, I can have many distributions, and all of these are expected to satisfy the constraint that summation of EI AI is equal to E. Okay. This is the third distribution.
What do the subscript and superscript?
I will tell you. Subscript is A suffix I, means number of systems with energy E1 in the first distribution. Okay. So, I can have 5 systems at energy E1. So, in one distribution, in another distribution I can have only 4, I have only 4 systems at energy E1. So, that is the second distribution. Then I can have some arbitrary number of, some other number of systems at energy E1, that is another distribution. There can be so many different distributions possible, isn't it? Yeah. So, that the suffix represents the energy, that is energy represents the energy, and superfix represents the specific distribution. If I, is that okay? No. Specific distribution. So, I have to give an example. So let us say the energy levels are 1, 2, 3 and 4, okay, and the total energy of the system is maybe say maybe 10, then I can have 10 systems in energy E1, 0 here, 0 here, 0 here. This is one distribution. In another distribution, I can have maybe 8 with this and one system with this energy, and still the energy is 10. This is the second distribution. So in this case, A12 is 8, A22 is 1, A32 is 0 and so on. And A11 is 10, A21 is 2 and so on. I can keep writing, and if I increase this number to a large value, you can imagine how many different distributions I can basically have, right? Huge number. Yeah.
What determines small d?
Any finite energy.
So that depends on what our total energy.
Actually I am writing it in a discrete manner. So it basically will depend upon the total number of the eigenstates that the quantum system has. Okay. So it depends on that. All possible energies that it can have. Okay. So you can have many distributions. So how many ways can a particular distribution be realized? So number of ways this particular distribution can be A1 superfix 1 distribution can be realized is nothing but n c taken A11 at a time multiplied by n minus A11 c taken A21 at a time, right? This is the combination, right? And you can keep writing, and this basically becomes n factorial divided by A11 factorial A21 factorial times A31 factorial and so on till AE1 factorial. This is the total number of ways a particular distribution can be realized. In a similar manner, I'm going to write this as this because this is a distribution. I am putting it in flower brackets just to emphasize the fact that it is a distribution. So total number of ways a second distribution can be realized will be again n factorial divided by A21 factorial, A22 factorial, A32 factorial, so on till AE2 factorial and so on. Okay. So what is the probability that you are able to find a specific distribution? Probability that we are able to find a specific distribution is nothing but number of ways that particular distribution occurs divided by all possible total number of ways all possible distributions can occur, right? Summation over H. HAK is nothing but the probability that a specific distribution can be realized, because it's nothing but total number of ways a particular distribution can be realized divided by total number of ways all possible distributions can be realized. We want to find out, again reminding you, we want to find out what is the total number of ways a particular system can have an energy EI, or what is the probability that a particular the system takes an energy EI. So that would nothing but be the average number of systems that have energy EI, right? Average, on an average, how many systems have energy EI divided by total number of systems will actually be EI, right? Or if you want to find out, this is how will you now, if you want to elaborate a little bit on this, what is the average number of systems with energy E1? If I find out, see, what is A suffix I? A suffix I is the average number of systems with energy EI, right? If I divide it by the total number of systems present, then I find out the probability that the system has energy EI. Now my task is to find out what is the average number of ways a system has, what is the average number of systems in energy EI. How will I find that out? How will I find out, for example, the average number of systems with energy E1? Not E1, not probability E1. So listen to the question carefully. I want to find out the average number of systems with energy E1. So basically A11 plus A12 plus A13 plus so on so on so on so on so on divided by total number. That is going to be the average number of systems with energy E1. That can also be written using probability in the following manner. A11 times the probability that A11 occurs plus A12 times the probability that A12 occurs, A13 times the probability that A13 occurs, in, right? But the probability that A11 systems are in energy E1 is nothing but the probability that the distribution occurs, isn't it? The probability that there are A11 systems in energy E1 is nothing but the probability that the A1 distribution occurs.